Welcome back, ladies and gentlemen. Mr. Eicher here. This is a part 2 of a lesson. We ended the last lesson talking about how you can tell the location of vertical asymptotes versus points of discontinuity in rational functions. So let's look at two examples, number 5 and number 7, and you'll do number 6 as a try this on Schoology. So first thing on number 5, we should factor the denominator. So factoring the denominator, we would get x times x is x squared, and we need to multiply to 6 to get to -5, so -3 and -2. Now notice neither of these factors, the x minus 3 or the x minus 2, neither one of those can divide out. There's no identical factor in the numerator, so that tells us we're going to have 0, no points of discontinuity, because nothing divides out. No factors divide out. For a vertical asymptote, though, we're actually going to have 2, and this might be the first time in this chapter that we'll have 2 vertical asymptotes. But we're going to set both of these factors equal to 0 and solve. So we get a vertical asymptote at 3, and we get another vertical asymptote at 2. So just quick idea, we'd have 1, 2, 3. We'd have a vertical asymptote at 2, and we'd have a vertical asymptote at 3. And we'll talk more later in this lesson and then the next lesson about what the graph is actually going to look like when you have 2 vertical asymptotes. Number 6 is for you, but let's look at number 7. Number 7, there's lots and lots of factors, but it's already factored for you. So first, let's see what factors will divide out. This -2, x minus 2, is going to divide with this x minus 2. So since those divide out, that gives us a point of discontinuity at the location of when x minus 2 equals 0. So that would be at x equals 2. And the directions say find the value of x for the point of discontinuity. So I guess that's it for that one. And then we have x plus 1 is going to divide with this x plus 1. So that tells you you have a point of discontinuity when x plus 1 equals 0. So that would be x equals -1. And when the dust is settled, our final simplified version of the function would be 4 over x minus 5, x plus 3. Notice there are no more factors to divide out. So these two factors, we're going to set those equal to 0, any factor in the denominator that's left over. And you could probably do this part in your head, right? Doesn't take too much to figure out that we would get 5 and -3. So we'd have a vertical asymptote at x equals 5, and we have a vertical asymptote at x equals -3. Now for the points of discontinuity, to find the y-coordinates, you weren't asked to, but I think it might be helpful to. To find the y-coordinates, you're going to use this simplified function right here, and you're going to plug in the x-coordinate that we found. So that would be 4 over 2 minus 5 times 2 plus 3. So that would give us 4 over -15. So we have a point of discontinuity at the coordinates 2, -4/15. You often get kind of weird fractions when you get the y-coordinate of the point of discontinuity. We do the same for the other x-coordinate of the point of discontinuity. So we're going to plug that into our simplified version. So that would be 4 over -1 minus 5, -1 plus 3. So 4/12 would be 1/3, -1/3. So we have a point of discontinuity at -1, -1/3. Another point of discontinuity. So we have 2 vertical asymptotes and we have 2 points of discontinuity. So we've been graphing what are called rational functions. Rational functions are in this form, p of x divided by q of x, where p and q are polynomial functions. We won't have anything like a log or a square root in these polynomial functions. And q of x cannot equal 0 since we can't divide by 0. So in this last part of the lesson, I'd like to help you determine when horizontal asymptotes will occur, or oblique or slanted asymptotes will occur. those depend on the degree of p of x and q of x, p of x and q of x. So the degree, you might remember, is the monomial term with the highest exponent. That would be the highest degree. So in our first example, focus way over here, if the degree is equal to, I've already highlighted it for you here, if the degree is the same for the top polynomial and the bottom polynomial, so this is what we're talking about, this degree right here, those twos are exactly the same, right? 2 is equal to 2. What type, how can we tell what type of asymptote that would be, horizontal or oblique? Well, that's going to be a horizontal asymptote. In the horizontal asymptote, what you do is you take the coefficient of each of these terms. So you'd have a horizontal asymptote at y equals positive 1/3, 1 over 3. So if this number up top had been a 4, then this would be a 4/3, would be the number that you're approaching. But it's not, it was a 1. The reason why that is if you plug a very large number in here for x, the squaring of the x is going to make that very large number gigantic. And all this other stuff doesn't change the value of the number all that much. So really, this squared term, the largest degree, is going to contribute the most to how the function is behaving. And then you can see that if those are contributing the most, if we divide out the x squareds, we get 1/3. So I'd encourage you, if you'd like, you can check out these functions on Desmos and see how they behave. And there will be a horizontal asymptote at 1/3. So that was one case. If the degrees are the same, what do we get when the degree in the top, the p of x, is less than the degree in the denominator, the q of x? So that would be this degree 2 is less than 5. So 2 is less than 5. Whereas on the previous one, 2 is equal to 2. So in this case, when you put very large numbers for x in, you would have all this stuff really isn't going to affect the behavior of the function much at all. So basically you're going to have a humongous number in the denominator because you're raising it to the 5th, compared to a, not as big number in the numerator. So what happens is when you have a small numerator and you have a big denominator, that is going to approach 0. So you can imagine like 1 over 1,000. That's really, really close to 0. So what we get is we get a horizontal asymptote at y equals 0, since 2 is less than 5. And then there's only one other case we've dealt with when the degrees are equal, when the top is less. What if the top is greater? So what if the top, that's a 2, is greater than the 1 in the denominator, which is understood to be 1. So what happens when the degree in the numerator is bigger than the degree in the denominator? Well, we would get an oblique asymptote. An oblique asymptote is a slanted asymptote. You can only have either horizontal or oblique. You can't have both. And the way we determine the location of an oblique asymptote is we use synthetic division, our good old friend synthetic division. So to set up synthetic division, we would have our positive 4 on the outside of our table. Positive 4 comes from the opposite of the negative 4 sign. And then we put the coefficients of the numerator at the top of the table. And you could pause the video and see if you remember how to walk through that process. But we'd drop the 1 down and multiply. We would add, we'd multiply, and then we would add. So these numbers down here, this is our remainder. These numbers tell us we started with the x squared. So this would be the equation y equals 1x minus 11, or sorry, plus 11. So location of the oblique asymptote is everything other than the remainder. So you get an oblique asymptote at y equals 1x plus 11. So those are the three things to look for when you're looking for, is it horizontal or oblique? So let's just practice one more time with an oblique asymptote, finding the equation, which we already did, but I'll walk through it one more time. You would use synthetic division. We would do the binomial on the denominator, which is a positive 4. We put the 1, 7, and 12, drop the 1 and multiply, add 7 and 4, multiply, and we get 56 is our remainder. So we started as an x squared. This now becomes a 1x and then 11 plus the remainder. But as you put very large x values in, the remainder approaches 0. So we would just have y equals 1x plus 11 is the location of the oblique asymptote. So I have a couple examples here, B and C, you'll be identifying on Schoology, and then 2 review questions, number 1 and number 2, just to make sure you don't forget how to divide and subtract rational expressions. But let's look at the first one as an example. What type of asymptote would each graph have? We would look for the highest degree in the numerator, so that's a 2, highest exponent, and then a highest degree in the denominator, that's a 3. So when you have a small numerator over a bigger denominator, right, 2 is less than 3, that would tell us we have a horizontal asymptote, or HA, at y equals 0. Now if they had been the same number, if they were both 3, then it would be the coefficients. You'd have a horizontal asymptote at 5/3. If the numerator was bigger, if you go big divided by small, that would give us an oblique asymptote. But that's not what we have here. We have the numerator smaller, the denominator is bigger, 2 is less than 3, so we would get a horizontal asymptote at y equals 0. And the next 2, if you'd like to do those right now, the next 2, you can identify those and then type your answers into Schoology. Thanks so much for watching this video. I'll see you next time.